we are finally to the titular, I don't know how to say that word. Titular part, anyway, we're to the linearity principle, which the name of which is this section. So let us get started, and we're going to start by going down and doing a little trip down memory lane. Do you remember differential equations that look like this? Way back when we only had one variable and one equation, those were the days, right? This was a linear equation, right? It didn't matter what a and b were. They didn't have to be linear. What mattered is y and dy dt were linear terms. Okay, and we solved these a few different ways, and one of the things that we said, which was really useful, is we talked about the linearity of this in such a way that if I have a solution to the homogeneous version, where b is 0, if b is 0, that's homogeneous. If I have a solution to the homogeneous version, then I can multiply that solution by any constant and still have, and that's the general solution to the homogeneous version of this equation. And then if I added any particular solution to this whole equation, that's the general solution to this non-homogeneous differential equation. And that was really useful because homogeneous were a lot easier to solve, and then I just had to find one particular solution. We did that with the guess and test method, or undetermined coefficients, which was much nicer when this was a constant. Anyway, we're going to do something very similar now, okay? But before we go into this, the book would like to give you a warning, okay? And the book is very serious sometimes. And it says, we are talking about linear systems right now, specifically homogeneous linear systems. This stuff is useful for other systems as well, but it doesn't apply directly. Okay, so we can use some of this for intuition. Some of this has extensions for other kinds of systems, right? And this is all valuable. You cannot use the linear principle willy-nilly. The textbook kind of says, using the linear principle is like backing your car out of the garage. You got to make sure it's in reverse before you put your foot on the gas. Otherwise, you're going to drive straight into your house. I'm sure all of us have houses, so it's very relatable and understandable. Yeah, so don't drive into a house. So make sure we're using principles, such as linearity principles, for what they belong with. Linear systems. All right, without further ado, what is the linearity principle? I'll tell you. Ready for another bit of writing here? So the linear principle, which is also known as the principle of superposition, which is kind of cool. Principle of superposition. I like it because it kind of sounds like superpower. Two names for it. And what that says is, okay, let's look at our traditional linear differential equation. dy dt is some coefficient matrix A times y, is a linear system of ODEs. Then we're going to be able to say two cool things about that, and we're going to be able to combine those two cool things to say a third cool thing. So it's like lots of cool things with one principle here. So let's say if I give you a solution, so if we have a solution here, then any constant times that solution is also a solution. Wow. You're either very excited or very not excited, right? Because this is the same. All right, we already had that for homogeneous solutions already, right? And this is a homogeneous differential equation. It's not ay plus b, it's just ay. Okay, so of course we knew that about homogeneous differential equations. Well, it turns out it's true for systems of equations as well that are homogeneous. And again, it makes sense, right? Because when you take the derivative of something, we can pull out constants. So if something satisfies this equation, then putting a constant here and a constant here, it's not going to change the truth of that equation. All right. Furthermore, this is also something useful if we have two solutions, okay, because there could be multiple solutions, and that doesn't violate uniqueness. We'll talk about why. If we have multiple solutions, then furthermore, if we add them together, it's still a solution. And again, this should seem very familiar to you, because it's kind of related to that. All right, and again, this should make sense. All right, if two things make this equation true, then as long as there's some kind of distributive property for matrices, and there is, then yeah, that should check out. All right. So we can combine these to say that if we have two solutions, any linear combination of those solutions will also be a solution. And before I maybe finish writing this down, what was a linear combination again? A linear combination of two vectors was adding the vectors up with any constants in front of them. All right. So for example, right, 2y plus 3y2 would be a solution. y1 minus y2 would be a solution. 5y1 plus pi y2 would be a solution, right? You can add together any combination of these, however many y1s you want and however many y2s you want, add or subtract them together, and that's still going to be a solution. And that's what the linearity principle says here, which is pretty cool. So let's verify something. Right? Let's verify that if k1 and k2 are any real number, and y1 and y2 are solutions to the equation we just wrote down, right? dy dt equals a times y. Verify that k1 y1 of t plus k2 y of t is also a solution. Right? How can we verify that linearity principle? Well, right, we know, what do we know? We know these are solutions. And again, could be good practice to pause the video and try to go through this all on your own. We know that those are solutions. That means the derivative of y1 with respect to t is equal to a times y1. And similarly, right, for y2. So that's what we know. What we want is we want the derivative with respect to time of this guy, right? We want this other thing to be a solution, so we need that derivative to equal a times that solution. And again, this does require a little linear algebra to say. Also, want. Does require a little linear algebra, but it's pretty straightforward because the left-hand side, right, we can essentially derivatives, right? We can put across addition as long as there's no infinities going on, and there are no infinities here. Constants can come out in front. So the left-hand side really is just k times dy1 dt plus k2 times dy2 dt. And we just said what dy1 dt was equal to, right? That's just a times y1. And dy2 dt, we just said, was a times y2. And we can't really do anything from there. I guess we could factor a little bit. But let's look at the right-hand side. And again, as long as there's some sort of distributive property for matrix vector multiplication, and there is, we really can just do this. And in fact, constants can also be pulled out in front. Interesting fact about matrix multiplication that I didn't talk about earlier is that, oh gosh, I should not talk and do this at the same time, is that matrix multiplication is not commutative. Okay, so, you know, we know that x times y is equal to y times x. That's not true for matrices. And in fact, some matrices, these don't even both make sense, right? Because to multiply matrices, you need that inner dimension to be equal to each other. Okay. But anyway, we do have some of these properties. So again, this is not really something you can verify without knowing properties of linear algebra, but I think they're pretty believable properties. And then again, so we're just going to hand wave our way through it. And if you want to take a linear algebra class, one's coming up soon, so you can take that. And that'll talk more about why this works. So again, we showed that the left-hand side and the right-hand side are equal to the same thing. Great. So hopefully you can get some idea of why any linear combination of solutions is also a solution. Because we just kind of showed why. Essentially because of the linearity of this stuff. Okay, so that's pretty much it for this video, I think. Let me check my notes. I always forget things. Yep, that's all I wanted to talk about. Last thing I want to talk about, actually, there's one little definition I wanted to include, is that this is a 2-param fam. Okay, this is what's known as gosh, I hate that. This is a 2-parameter family of solutions. Right? It's a family of solutions because there are infinitely many of them. It's a 2-parameter family of solutions because there are 2 parameters that define that family. Think back to bifurcations. We had 1-parameter families of differential equations. Those 1-parameter families of differential equations look something like dy dt was some function of alpha of y. This was an autonomous differential equation with 1 parameter in it. We called this a 1-parameter family of differential equations. Right, is a group of differential equations with 1 parameter. So here's a 2-parameter family of solutions. All right, just a little bit more definitions because I'm sure you needed more definitions in this section. And we've gotten most of them out of the way. The last 2 videos for this section are really just solving some problems so we can finally use some of this. Right, we talked about a lot of theory. We introduced a linearity principle that said, okay, if I have 2 solutions, I can get any linear combination of those will also be a solution. Let's use that very powerful thing. We use that with our notation. We use that with our knowledge of how equilibria work, with how many equilibria there's going to be for these linear systems, depending on whether the determinant is singular or not. And so it's time to use the stuff that we've talked about, which is usually the more interesting thing. Get ready, take a breath, grab some water, move around, leave, and I'll see you there.